Hello. In this video, I'm going to talk about the solid design patterns. Seems to be a thing these days and a common interview question. What are the solid design patterns? And they're just 5 general principles to follow when designing code or architecting out a system. So let's take a look at them. So we have the single purpose pattern, the single use pattern, the open close pattern, the Liskov substitution principle, interface segregation, and dependency inversion. There you go. So you can see that solid is, oh, I forgot what they call that, an acrostic or something. So the first letter, it's a word made up of the first letters of the different patterns. So there we go. There's just 5 different patterns, and now we'll go through these patterns and talk about what they are, because I found some funny slides online that kind of illustrate these things and why you should follow them. So the first one is the single responsibility principle. And what you don't want to do is design something that looks like this. So the idea with the single responsibility principle is that an object has just one responsibility, or there's one thing that it does, and that all its functions are aligned to that. We're not trying to make one object that does everything. And that makes sense, but usually when you start a project and then some new requirement pops up and you say, okay, well, hang on, I'll just extend the main class to do a little bit, or I'll add a little bit more here, a little bit more there, a little bit more there. And suddenly that main class that was just maybe running the interface before, now has got business logic in it. It's responsible for importing files and maybe doing connections to a database or something like that. It's suddenly doing a lot more than it was originally designed to do, and it's doing many different types of things. And that makes it kind of hard to maintain, and it also makes it hard for multiple people to work on it simultaneously. So that's why you want to follow the single responsibility pattern. Just think of, if anybody asks you what it is, just say it's the idea that a class has one thing to do and all of its functions are aligned to that goal. I mean, a good example of this is the math class, right? It's a class that has nothing but math functions in it. So there's a great example of a math function, or the single responsibility pattern, right? You wouldn't put file IO stuff in the math class. You just wouldn't, right? Because you look at that name, you're like, oh, this class is for math things. It has a single responsibility. All right. If you don't follow this pattern, you end up with a bunch of other things called anti-patterns, and they're kind of bad ways of doing things. They have a bunch of different names. There's the God object. It's the object that does everything. The kitchen sink object, or a Swiss Army knife object. So Swiss, and not the one that has just the tools you need, the one that we saw in the previous slide. So if you don't follow that, you end up with the kitchen sink object. The open close principle. Chest surgery is not needed when putting on a coat. What does this slightly creepy and disturbing slide mean? Well, the open close principle says that classes should be open for extension but closed to modification. What does that really mean? Okay, well, it means that we should be able to change or create subclasses to change the way an object works, to change an object's behavior, without having to hack the core code of the original object. And that gets back to this, like, I shouldn't have to go cutting somebody's chest open to put a coat on them, right? I shouldn't have to hack the core of an object to go subtly, slightly modify its behavior to handle a new use case. So how does that work in C#? Well, we've learned about public functions and we've learned about virtual functions. So if an object has public virtual functions, new objects can come along and override those and provide new implementations for behavior. They can handle new business cases that pop up through making subclasses. That's how an object is open for extension. It means you can extend the methods that it provides to make it do new things. What does the closed part of that mean? Well, it means we can't hack the core code of that thing. It means that, and ideally what you'd want to do is create a class that had a good public interface that was going to be flexible enough to account for new circumstances that might come along. You make them virtual so people can override them. But then you take that core code, you compile it, and you put it in a DLL, and then no one can even go in and modify the original source code even if they wanted to. So you've closed it off to being hacked at the core. Right? Thou shalt not hack the core is what we're going at here. We should be able to add new behaviors to an existing object without having to modify the core code of the original object. That's what the open-close principle is. And I just talked about this, right? Take an object, give it an interface that it exposes using either an interface or public virtual methods, compile the thing, put it in a DLL, then other people can come along and extend it. All right, pattern number 3, the Liskov substitution principle. If it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. That's not really entirely clear to me what that means, but I can tell you what the Liskov substitution principle means, and that is about substitutability of objects and the protection of interfaces. So if you look it up on Wikipedia, you'll see something like this. If object B is a subtype of object A, which means B inherits A and B is an A, then I should be able to substitute a B object wherever an A object was being used without having the code break. Like I shouldn't have syntax errors about functions not being available or provided or implemented. So this new B object, maybe it's overriding functions and it's doing things a little differently than A would have done them, but the interface is still there. So B provides the same interface that A does. Subtypes are guaranteed to implement the same interface that any of their base classes implement. That's what we're going at here. The substitutability works because the interfaces don't change. You can't remove a function from an interface is kind of what we're going at here. And fortunately, C# actually supports this. So it's kind of a trick question. But I don't know about other languages. Like in Python, maybe it's possible to break the Liskov substitution principle. So imagine object A here, the base class, has some public virtual methods in it, and then I create a subclass of it, and I redefine some of those public virtual methods to be private. Well, can I then substitute a B wherever an A was used? Well, no, because some of the stuff that was publicly exposed in A is now gone. It's not publicly exposed anymore. So I couldn't substitute a B for an A. So that would be a violation of the Liskov substitution principle. Kind of a flip side to this is I shouldn't be able to take anything in A that's private and make it public. I can't take something that was originally closed off by the base class and expose it and open it up. And that's just basic security stuff. Like, what if, I mean, things are private for a reason. They have to do with like an object protecting its state. Or what if there's a security library that has a private function in it that matches passwords? Should I then be able to subclass that object and provide a new implementation that's public that I can then go modify? So maybe it doesn't do password checking, so I can hack into somebody's account. Well, no, right? If the base class says this thing is private, you can't go override it and say, you know what, sorry, I'm going to make it public now. So if something is private in the base class, it stays private. If something's public in the base class, it stays public. The interfaces are protected. That's why the Liskov substitution principle, or that's how the Liskov substitution principle remains intact. You're protecting interfaces by making sure that functions are not added or removed from them. So and that's how the substitutability works. I can substitute a B for an A because a subclass is guaranteed to implement the same interface as its base class, at least. A B will at least have all the members of an A. That's the Liskov substitution principle. All right, this one is a little weird. The interface segregation principle, you want me to plug this in where? Okay, so we've got a box with a lot of different plugs and buttons and adapters and a key. So what's going on here? The interface segregation principle. Well, the interface segregation principle, simply put, says it's better to have a lot of small interfaces with clearly defined functionality than fewer large interfaces. This is really the single purpose or single use pattern applied to interfaces. And this principle actually arose out of a real world case where there was a banking system that was running incredibly slowly, and a software engineer went in and looked and figured out what was going on. And this was the reverse engineering of the objects in that banking system. And what we've got here is some transactions that are concrete transactions that implement or subclass inherit from a transaction object. This transaction object implements an interface. And if you notice here that the deposit transaction now has access to these request transfer amount, and a transfer transaction has access to this withdrawal stuff. So what's happening is here is a transfer transaction is much larger than it needs to be because it's got to provide all this stuff that it doesn't use, or at least it has access to all this stuff that it doesn't use and doesn't need. So the problem here is that this interface here is too big. We've got one interface that's handling it looks at least 3, possibly 4 different types of transactions. So this is the kitchen sink problem, or the God object, or the Swiss Army knife problem applied to interfaces. We have one interface that's trying to do everything. And the better solution is to break that one interface up into a lot of smaller interfaces. So rather than having one interface that does a whole lot of things, now we've broken this thing up into 3 interfaces, and now our objects can be smaller and much more easy and cleaner and easier to maintain. So that's the interface segregation principle. It's really the single-use, single-purpose pattern applied to interfaces. Interfaces should have be aligned to one particular task, and that's it. Everything, all the functions in that interface should be aligned to that task. That's what the interface segregation principle means. All right. And then again, I mentioned this before, the Swiss Army, here, I can just read this thing. So a Swiss Army knife, also known as a kitchen sink, is an excessively complex class interface that a designer attempts to provide for all possible uses of the class. In the attempt, he or she adds a large number of interface signatures in a futile attempt to meet all possible needs, right? If this happens as a result of feature creep, and at some point, somebody needs to come in and say, you know what, this object has gotten too big and too clunky, and it's too complicated, and no one can figure out what it does, so let's break it up into smaller objects. Dependency inversion principle. I love this one. Would you solder a lamp directly to the electrical wiring in a wall? Well, the answer is, of course, no. So how does that weird description, what does that mean? What does that mean to us? What is it? Why don't we solder a lamp to a wall? Well, the idea is that objects should not be chained to their dependencies. That objects should be given their dependencies. They should not be hardwired. Dependencies, something an object needs, should not be hardwired into that object the same way we would not hardwire a lamp to an outlet. And let's look at some simple examples here. And I think you'll agree that the dependency inversion principle is something that we should follow. As I said before, high-level objects should not be chained to a specific implementation of objects they depend on. Objects should depend on abstractions, which means interfaces, not specific implementation, which means concrete types. So the lamp should not know that it needs to be plugged into a specific power outlet. All it knows is it should really all it should know is that, okay, you know what? I just need a 120 volt supply. That's it, right? Now, I don't care which one. I just need I need something that provides me 120 volts. That's it. And let's look at an example here of kind of the wrong way to do this. So this is an example that doesn't follow the dependency inversion principle. So imagine that I have a class called Customer Record System, and in here I have a private database called SQL Database, and the name of that variable is DB. So SQL Database in this example is a concrete type. There's a class called SQL Database, and in this constructor, we make that database, and now we have it available to us. So I mean, this works in the sense that the program starts up, it creates its database, and then it can do stuff. But the problem is that this customer record system depends on this database. This database is one of its dependencies. And here this object has been hardwired to this particular type of database, which makes this program really very inflexible. And so what the dependency inversion principle says is we shouldn't have a specific type of database here. We should have an interface or a base class here, and then somebody else externally should supply us with our dependencies. Our dependencies should be given to us from the outside, and we shouldn't know what specific type of object they are. We should just know that they implement an interface, or they're a base class. They've got a list of functions in them that they're guaranteed to implement. So let's take a look at a better way to do this. I mean, makes sense, right? But the problem is that it's not flexible. So let's skip this slide here. Okay, there's a better slide. So imagine that we've got a class called iDatabase. This is a base class with maybe it's an abstract class. It's got some public virtual methods in it for connecting, retrieving records, updating, deleting, disconnecting, the standard CRUD stuff. Was it create, retrieve, update, delete, CRUD operations? And then imagine we could subclass that. We could have a fake database that's just used for testing. It's just fake customer data. We just want to test the business logic because we don't want to test business logic using real data. And then when we go live, we can give this thing a real database. We'll have a real database class that implements this interface. So we've got two different objects here. They both implement the same set of functions. They provide the same list of public functions. They're interface, right? So now our customer record system can just know that it has an iDatabase and not worry about what subtype it's got. It just knows that this object that's been given implements the iDatabase interface or a bunch of public functions through polymorphism, and it can interact with that, and it doesn't need to know what the subtype is. So let's look at what that would look like in our class. We'll make a class called Customer Record System here, and we'll have a private database here, but notice this is an iDatabase. This is an interface. We don't know what specific type of object this thing is. We don't care. As long as it implements the iDatabase interface, and I think that should be a capital B, we're okay. And then let's provide a property. We'll make a public property called DB, and we'll make it a set-only property. So we can set our database. Or somebody else can set our database to be a particular object that implements the iDatabase interface. Somebody else external to us will set the customer record systems database to be any database type that implements that interface. And then we could do something like this. We could create a customer record system, and then we can create a new database and assign it to the customer record system. We can say, hey, customer record system, here's your database, go. Right, so here we're making a new test database, and as long as that implements the iDatabase interface, we can assign it to DB. Or we could make the real database, so that's real customer data interface, and assign it to the customer record systems database, right? So the idea is somebody outside, the class isn't finding its dependencies, it's going, somebody external to an object is supplying the object with its dependencies, and the interaction is based on interfaces rather than knowing that an object or a dependency is of a concrete type. We want to rely on interfaces and polymorphism rather than knowing the specific types of objects. So that's it. So this is called dependency injection, is when an object is supplied its dependencies at runtime. This is often done with a configuration file. An application starts up and or an application is started up and a configuration file is read, the objects are created and then supplied to the new running process. So a server will kick off a process and be like, okay, process, based on your configuration file, I've now created all your dependencies and I'm giving them to you, go. So the idea is we've got loose coupling here. Objects don't know the exact types of the objects that they're communicating with because they're communicating through interfaces, and this allows us to be much more flexible in the way we use objects. So there you go. There's the holy grail of this. The whole thing, the whole point of this is to get to this point of dependency injection. We supply objects with their dependencies so they don't have to go create them using concrete types. So that's it. Those are the 5 solid design patterns, and that seems to be a common interview question. So let's just go back to that very first slide, all the way back at the beginning. There we go. There's our 5 patterns: single purpose, open closed, Liskov substitution principle, interface segregation, and dependency inversion, right? And the whole point of dependency inversion is to get you to dependency injection. That's a really slick way to do things. So there you go. I hope you find this useful, and I hope this comes up on your interview, and then you'll have all the answers and you'll be a rock star and have a good job. Your life will be happy. All right. Thank you.